The type of calorimetry that we do at constant pressure is called coffee cup calorimetry. So a coffee cup calorimeter is just a double layer of styrofoam cups that we can run a reaction in, measure the temperature, and then get the heat from the reaction under constant pressure conditions. So we'll have these double layer, double stacked styrofoam cups. If you do this in the lab here at WashU, we also put some sand in the bottom to weight it down so that your cups don't fall over. This has a lid, a stir rod, a thermometer, and then it has a reaction in a solution that is inside the cups that the thermometer is down in, that this is what we are measuring the temperature of. And inside this coffee cup calorimeter, right, the reaction is dissolved in the solution. The reaction is the system. The solution is the surroundings. Now, the solution is probably mostly water, since we do all aqueous reactions in general chemistry. So probably we're going to treat it with all of the information that goes with water, but everything is mixed together, but that encompasses the system and the surroundings. Everything else on the coffee cup calorimeter is just designed to insulate it from the outside to make sure that all of the heat that's transferred as the reaction happens is into or out of the solution, since that's what we're measuring the temperature of. So the way that we do this is we measure delta T for the solution, right? So Q equals MC delta T for the solution. And then because it's insulated, the heat of the solution is the same magnitude but the opposite sign as the heat for the reaction. So the heat for the reaction is then the heat at constant pressure, which is the change in enthalpy of the reaction for the mass reacted, right? This now also depends on the amount that we put in. Let's look at an example. So we have 0.158 grams of magnesium combined with enough hydrochloric acid to make 100 mils of solution in a coffee cup calorimeter. All of the magnesium reacts and gas bubbles appear. The temperature rises from 25.6 degrees to 32.8. The solution has a density of 1 gram per mil and a heat capacity of 4.184 joules per gram degree C. Find delta H reaction for 1 mole of magnesium. And I've given you the balanced reaction here. You could do this without the reaction, but the reaction happening is that magnesium is reacting with hydrochloric acid to make magnesium chloride and hydrogen gas. So for my solution, which is what I have the temperature measurements for, there's 100 mils of solution, which means I have 100 grams because my density was 1. My specific heat capacity is 4.184 joules per gram degree C, and my delta T is 32.8 minus 25.6. This gives me a value of 3,000 joules of heat absorbed by the solution for that 0.158 grams of magnesium. So Q solution is the opposite of Q reaction. So my Q reaction is negative 3,000 joules for that specific amount of magnesium. I want this in joules per mole. So my 0.158 grams of magnesium converted to moles is 6.499 times 10 to the minus third moles. And negative 3,000 joules divided by 6.499 times 10 to the minus third moles gives me negative 4.6 times 10 to the fifth joules per mole of magnesium.